Very good evening, children. So today let us see the 13th chapter, class 12, that is nucleus. So already you have learnt in class 10 about the nucleus, atom, the orbit, the proton, neutron, electron, all that. Just the continuation. So now what is the core concept behind, what is the learning outcome behind this nucleus lesson is only the binding force. So the major part of the lesson covers the binding force. So come, let us learn about the nucleus, and let us have a recapitulation of the nucleus lesson, what we have already learnt in chemistry as well as in physics in the lower classes. Okay, children. So can you recall and tell me in nucleus? So in the nucleus, in an atom, we have nucleus at the center. In atom lesson also we have learnt about Rutherford alpha particle scattering experiment and Bohr's postulate. So in that, nucleus will be at the center, and to find the size of the nucleus, right? So alpha particle scattering experiment, can you recall all that? So when alpha particle is subjected to, or alpha particle is allowed to fall on the gold nucleus, so what happens? Scattering takes place, and from that scattering he was able to find out the distance of close approach, hence roughly was able to estimate the size of nucleus. And also some observation and conclusion we have already studied, and it says that most of the space in an atom is empty because the nucleus size and the atomic size, the atom is very huge, 10 power 5 times it's larger than the nucleus size, and of course both are microscopic. So size of the nucleus in atoms lesson is roughly about 10 power minus 15 meters. And what about the size of an atom? Size of atom is roughly about 10 power minus 10 meters. So from this, what you can understand, you understand that atomic size is larger than the nucleus size. Most of the space in an atom is empty. So now coming to this, nucleus is a positive charge. So nucleus inside, what will be there? Proton and neutron will be there. Okay, proton and neutron will be around the nucleus. What will be there? Electrons will be revolving around it. So this is the electron which is revolving around the nucleus. I have already told you, view in such a way that there is a vast space. So there is a large distance between the center of the nucleus and the first orbit and second orbit, so on. But then also there is a huge energy which bind the nucleons together. So proton, neutron is present, the electron is revolving around it. Electron is a negative charge and nucleus is a positive charge, so there is a strong Coulomb's force which exists between that, all that we have learnt. Now coming to this nucleus, first and foremost thing what we are going to learn is about isotopes, isobars and isotones. So let us learn about that first in nucleus lesson. Okay, so first, what are isotopes? What are isotopes? Isotopes are nothing but elements having, I'll just go to the next page and then write, having isotopes. You can have a differentiation between that. Isotopes, elements having same atomic number, same atomic number, different mass number, so that is called as isotope. Example, I can take hydrogen isotope itself, same atomic number, different mass number, H12, isotope of hydrogen, deuterium and tritium. Simple example you can give. Next is isobar. Isobars are nothing but elements having same mass number and different atomic number. Now Same mass number, different atomic. So I can take H13 and He23. Isotope of hydrogen, isotope of helium, same mass number, different atomic number. Next one is isotones. Even calcium 40 also you can take. So 40 is a mass number, right? So anything which is having same mass number you can always take. So isotones, example. Isotones are nothing but elements having same number of neutrons. Same number of neutrons. Elements having same number of neutrons. So example, same number of neutrons, right? So if I take H12, so what is the number of neutron? Mass number minus atomic number. Similarly, I can take He23. So here 2 minus 1 is equal to 1 and here 3 minus 2 is equal to 1. So therefore same number of neutrons, hence isotope of hydrogen deuterium and isotope of helium 2, 3. So that is considered to be isotope. So these are the just basic which you have learnt. And the next one is, what are nucleons? What are nucleons? 1 minute, children. So let us see what are nucleons. Inside the nucleus, protons and neutrons are present, right? Inside the nucleus, protons and neutrons are present. That protons and neutrons come together, you call it as nucleons. So let me write here, inside the nucleons, inside the nucleus. Inside the nucleus, protons and neutrons are present. Protons and neutrons are present. The protons and neutrons all together you call it as nucleons. Protons and neutrons constitute nucleons. Protons and neutrons constitute nucleons. So what are nucleons? Proton and neutron together called as nucleons. Always let us take mass of one nucleon. Mass of one nucleon, which is constant, is nothing but mass of one proton plus mass of one neutron. So which is always a constant, which is taken to be m. So all this basic we have learnt. Now let us say about carbon atom, which is so special. In chemistry also you have learnt. So different mass unit is used for atomic masses. So unit of atomic mass. So unit of atomic mass. So unit of atomic mass is otherwise called as 1 atomic mass unit. That is nothing but 1 AMU. This unit is the atomic mass unit, which is defined as 1/12 of the mass of carbon 12 atom, which is defined from the basic element called as carbon atom. 1/12 of the mass of the carbon atom, because mass of the carbon 12, the pin carbon 12 has mass, atomic mass 12. So 1/12 of the mass of carbon atom is defined as 1 atomic mass unit. So 1 unit is equal to, that is 1 atomic mass unit can be written as 1 U. Mass of 1 carbon 12 atom divided by 12. What is mass of 1 carbon 12 atom? 1.992647 into 10 power minus 26 kilogram divided by 12. So that can be written as 1.66 into 10 power minus 27 kilogram. So always keep it in mind, 1 atomic mass unit is style, you write it as 1 U, which is 1.66 into 10 power minus 27 kilogram. That is the unit of 1 atomic mass unit. So now coming to the discovery of neutron. Where is neutron present, children? Inside the nucleus. Olden days, we were not sure about what is present apart from the proton. Already we learned from Rutherford alpha particle scattering experiment, only a cloud of massive positive charge, a small space, it is present, that is called as nucleus. So it was only repelling, so from that he was able to conclude that nucleus contained positive charge. But we were not sure about what else was present apart from the proton. So now discovery of neutron made us to understand that there is another uncharged particle that is present. So that is responsible for binding up the nucleon together. So let us see. Since the nuclei of deuterium and tritium. So what is deuterium? H12. What is tritium? That is H13. Or the isotopes of hydrogen. They must contain only one proton each. H12. Proton is equal to number of protons. What is the, children, number of protons? This is mass number. This is atomic number. Now you tell me what is the number of protons. Number of proton is equal to 1. Whereas in the case of H13, how many number of protons? There also it is 1. Number of protons. There also it is 1. Okay, right. Then, but the masses of the nuclei of hydrogen, deuterium and tritium are in the ratio of 1:2:3. This is hydrogen, that is protium, deuterium, tritium. All atomic number is same. But when you see the masses, the ratio is 1:2:3. The ratio is 1:2:3. Therefore, the nuclei of deuterium and tritium must contain, in addition to a proton, some neutral matter. So, the amount of neutral matter present in the nuclei. Why neutral matter? Because the number of protons is equal to number of electrons, the atom as a whole is neutral. So, that means there must have been some other particles which is present which has to be neutral. So, the amount of neutral matter present in these isotopes expressed in unit of mass of a proton is approximately equal to 1 and 2. In terms of mass of the proton is approximately equal to 1 and 2 respectively. This fact indicates that the nuclei of atom contain, in addition to proton, neutral matter in multiples of a basic unit. In multiples of basic unit. This hypothesis was verified in 1932 by James Chadwick, who observed the emission of neutral radiation when beryllium nuclei were bombarded with the alpha particles. So he was able to find out. Earlier the people were used to tell that, oh, the particle which is present inside the nucleus must have been some photon because it is emitting energy. So radiation it is emitting, so must have been, it is photon. But research found out that, experimental results, the conservation of energy found out that the photon energy is greater than that of the energy possessed by this beryllium nuclei. So here alpha particle and beryllium nuclei. So that the law of conservation of energy was violated. So hence Chadwick found out that, later on he was able to find out that it is not absolutely called as photon. It is not photonic radiation. It is something else. So he named this as neutral particle called as what? Neutron. So come, let us see. So in 1932, James Chadwick, who observed the emission of neutral radiation when beryllium nuclei were bombarded with alpha particles. It was found out that this neutral radiation could knock out the protons. This neutral radiation that's already present, knock out the protons from lighter nuclei such as those of helium, carbon and nitrogen. The neutral radiation known that at that time was photon. At that time it was named as photon, electromagnetic radiation. But Chadwick was able to sense it, was able to find out. Application of the principles of conservation of energy and momentum showed that if the neutral radiation consists of photons, if it is going to be a photon, the energy of the photon would have to be much higher than the available from the bombardment of beryllium nuclei with alpha particle. So the energy obtained, the law of conservation of energy says that the amount of energy of the reactant should be equal to amount of energy of the product. So energy of beryllium and alpha particle should be equal to the parent nuclei of the energy should be equal to the daughter nuclei which is delivered but it is deviating. So it's violating. So therefore he was able to conclude that must not have been photonic energy, and the clue to this puzzle which Chadwick satisfactorily solved was to assume that the neutral radiation consists of new type of neutral particles called as what? Neutron. So who found out neutron? That's all, the whole paragraph. Who found out neutron? Neutron was found out by James Chadwick. Who found out neutron? Answer is James Chadwick. So how he was able to conclude that is neutron? Because beryllium, when it is bombarded with the alpha particle, releases some amount of energy that earlier days, in olden days, it was called photon energy. But the law of conservation of energy and law of conservation of momentum has been violated. Hence he was able to conclude that it must not have been photon, must have been the neutral radiation consists of new type of neutral particle called as neutron. And the mass of the neutron is nearly equal to the mass of the proton. So that is equal to 1.67 into 10 power minus 27 kilogram. So hope you understand, children. So what is the learning outcome of this discovery of neutron? Very simple. Nucleus contained a neutral particle. That neutral particle, earlier it was called as photon energy, but then James Chadwick was able to prove that it is violating the law of conservation of energy and momentum. Hence he named this radiation, neutral radiation, called as neutrons. That is all, children. Next. Chadwick was awarded 1935 the Nobel Prize in Physics for his discovery of the neutron. Who discovered neutron, I should say. Who found out. It's not a correct word. Who discovered. Discovery. So who discovered neutron? James Chadwick. Okay, right. Now, Chadwick was awarded 1935 the Nobel Prize in Physics for his discovery of neutron. Now come to the point. A free neutron, unlike a free proton, is unstable. So you can say as long as inside the nucleus, it may be stable. But if it is freely available, one solo neutron is always unstable. Free neutron is unstable. Therefore, to attain stability, unstable, to attain stability, in order to attain stability, it has to release a proton, it has to decay into proton, electron and antineutrino. Then only it will attain stability. So once again let me repeat, one neutron is unstable. In order to attain stability, it has to release one proton, that is proton is nothing but H, plus one electron with negative charge, one antineutrino, chargeless, massless particle. This is called antineutrino. So you can call it as chargeless, massless particle. Chargeless, massless particle only release energy. So one neutron is basically in nature, free neutron is unstable. A free neutron, unlike a free proton, proton is stable, but free neutron is unstable. In order to attain stability, it decays into proton, electron, antineutrino. Antineutrino is another elementary particle and has a mean life of about 1000 seconds. Mean life. Only can exist about 1000 seconds. After that it vanishes. It is, however, stable inside the nucleus. It is unstable only if it is going to be free. But neutron is stable inside the nucleus. Neutron is stable inside the nucleus. Where? Inside nucleus. You got it, children? That is all the learning outcome here. You know about. And we know that Z is the symbol for atomic number, N is the number of neutron, A is the mass number. So MP is equal to mass of the proton, and Mn is equal to mass of neutron, and capital M is equal to mass of the nucleus. So all these are just a symbol. So now let us go to the next one. Here, the composition of isotopes of an element can now be readily explained. The nuclei of isotopes of given element contain same number of protons. So recap about isotope, isobar and isotones. I have already told you same number of neutron. So that is what. Now here, give the mass of ion nucleus. Now I am going to talk about this nuclear density. So nuclear density I am going to talk. Before that, there is a very important, interesting topic over here. Elementary topic. In the scattering alpha particle experiment, we know that the distance of close approach to a gold nucleus of alpha particle possesses the kinetic energy of 5.5 mega electron volt. That distance of closest approach comes around to be 4 into 10 power minus 14 meter. This is for alpha particle. What is the kinetic energy possess? 5.5 mega electron volt. The scattering of alpha particle by the gold sheet could be understood by Rutherford by assuming that the Coulomb's repulsive force was responsible for scattering. Because alpha particle is positive, nucleus is positive, when it comes no closer, a strong repulsive force exists, therefore alpha particle goes back. So that distance of close approach only is found to be 4 into 10 power minus 14 meter. But if we use alpha particle of higher energy than 5.5 mega electron volt, we know that distance of close approach is equal to 2k Z e square divided by half m e square. If we increase the kinetic energy, the distance of close approach will be very small because inversely proportional. So therefore, the distance of close approach to the gold nucleus will be smaller, and at some point the scattering will begin to be affected by the short range nuclear force. So when you come closer and closer, what will happen? The Coulomb's repulsive force would have been nullified, would have been negligible, whereas a strong force which is existing between the proton and neutron will dominate. Only till some distance, this is nucleus, only till this distance there is a possibility for repulsive force to be dominating alpha particle. But when you come very closer, the Coulomb's repulsive force would have been weakened, and the nuclear force is there, no, that get escalated. That means that would have been dominating over here, nuclear force. What are nuclear force? That we are going to study now. So therefore, Rutherford calculations are based on pure Coulomb's repulsion between positive charge of the alpha particle and gold nucleus. By performing the scattering experiment with which fast electrons instead of alpha particles or projectiles that bombard target made up of various elements, the size of the nucleus, various elements have been accurately measured. Already what we measured with the help of Coulomb's repulsive force. By taking alpha particle, instead of alpha particle we take fast electron, and it has been found out that the distance, the nucleus of mass number A has a radius, the nucleus of mass number A has a radius r is directly proportional to a power 1 by 3. That distance is there, no, the distance, that means the radius of the nucleus is directly proportional to mass number. So he says that more the mass number, more is the radius. Till such a point, the Coulomb's force, the nuclear force dominates. Where R0 is equal to 1.2 Fermi, this means that the volume of the nucleus is proportional to R cube. So let us see that size of the nucleus. So now we are going to see the size of nucleus. So size of the nucleus is directly proportional to nucleus. I am not talking about atom, it is nucleus. Size of the nucleus is directly proportional to mass number A. That's nothing but volume of the nucleus. Okay. So now size of the nucleus is directly proportional to volume of the nucleus. volume of nucleus. What is volume of the nucleus? 4 by 3 pi r cube. So we have seen here, just now we saw, it has been found out the nuclear mass number has the radius r is equal to r naught a power 1 by 3. So same thing I am going to take it. So how am I going to take it here? We know that volume of nucleus is equal to 4 by 3 pi r cube. But this r is directly proportional to mass number. R is directly proportional to A. So therefore, r cube is directly proportional to a power 1 by 3. Because r cube is directly proportional to a, r is directly proportional to a power 1 by 3. Because I have to say that volume of nucleus is directly proportional to mass number. Just now we have seen, no. So therefore I am writing like that. So volume of the nucleus 4 by 3 pi r cube is directly proportional to mass number. So therefore I can write it as r cube is directly proportional to, just one step I have left it, I will write, I can write r cube is directly proportional to a. So r is directly proportional to what? A power 1 by 3. Could you understand, children? Once again let me repeat. We have already discussed here, it has been found out that the nucleus of mass number a has the radius r naught a power 1 by 3. The volume of the nucleus is proportional to r cube. So that means the volume of the nucleus is directly proportional to mass number. More the mass number, more is the volume. It's truly correct, right? So volume of the nucleus is 4 by 3 pi r cube is directly proportional to A because we are considering as spherical nucleus. Or you can write r cube is directly proportional to A. What is r? R is the size of nucleus. Size means radius. Radius of nucleus. So therefore, taking over the proportional to a constant r is equal to r naught a power 1 by 3, where r naught is called as distance of closest approach. Can you see here, we've seen r naught is nothing but distance of closest approach. So therefore here r naught is equal to distance of closest approach. Now we are not taking alpha particle, please keep it in mind. What we have taken, fast electrons. So therefore you can say here distance of closest approach, and this value is equal to 1.2 Fermi. See here 1.2 Fermi, same thing here. So that is nothing but 1.2 into 10 power minus 15 meter. But with the help of the alpha particle, what have we seen? 4 into 10 power minus 14 meter or 4 into 10 power minus 14 meter or 40 into 10 power minus 15 meter, but for this kinetic energy 5.5 MeV. But if you increase this kinetic energy, what will happen? The distance of close approach will reduce and this Coulomb's repulsive force domination will be nullified. Not nullified, is actually negligible, whereas nuclear force dominates. So hence we found out like that. So now let us see the nuclear density. This is also very, very important topic. Nuclear density. So we know that nuclear density is nothing but rho. So nuclear density, inside the nucleus, what is there? Inside the nucleus, neutron, and what else is there? Proton. Neutron and proton together, what is it called as, children? We have already seen here. One neutron and one proton, what is it called as? Check here. One neutron and one proton together, you call it as nucleon. So we are going to talk about only that. Nuclear density is nothing but nuclear density. Nuclear density rho is nothing but mass of all nuclear. Listen here carefully, children. What am I writing? Don't simply write mass by volume. Mass of all nucleons. I am not talking about one proton or one neutron. Mass of all nucleons by volume of nucleus. Volume of nucleus. So that is nothing but, what is, how many nucleons are present? One nucleon mass is m. So therefore mass of all nucleons is nothing but m into a. So because mass of all nucleon is equal to, you can write Mass of all nucleon is equal to mass of one nucleon. One nucleon into total number of nucleon, that is nothing but mass number whole divided by volume of the nucleus, 4 by 3 pi r cube. So you have to be very careful. M into A divided by 4 by 3 pi into, instead of r cube what can you write? Previously you wrote no here. What is r cube we wrote here? R is equal to r naught a power 1 by 3. Same thing I am writing. So r naught a power 1 by 3 whole cube. So what will happen now? So therefore rho will be equal to ma 4 by 3 pi into r naught cube into a. So a get cancelled. That is all. Everything is going to be constant. M by 4 by 3 pi into r naught cube. Children, mass of one nucleon is constant. We have already seen that. Mass of one nucleon is constant. What is M? M is equal to mass of one nucleon. What do you mean by one nucleon? Careful children. One nucleon is mass of one proton and one neutron. And one neutron. So therefore that is constant. That's equal to constant. And of course R naught is constant. That is 1.2. Fermi is constant. Everything is constant. Therefore nuclear density is constant. What is nuclear density? 2.3 in 10 power 17. 2.3 into 10 power 17 kilogram per meter cube. That is nuclear density, children. So thus nuclear density is independent of the mass number. Check here, mass number vanished. So thus nuclear density is there, no? Nuclear density is independent of mass number. So therefore whether it is small nucleus or it is bigger nucleus, for example copper atom, for example hydrogen atom, what is the nuclear density for copper atom and nuclear density for hydrogen? Both the same. Density remain the same. So I am taking water in a beaker. I am also taking water in a tumbler. Only the volume of the water in beaker and tumbler is different. Density remain the same. No, same thing here. Nuclear density is independent of the mass number. So that remains same. Remain the same for all nucleus. For all nucleus. So therefore, what is the nuclear density ratio? Ratio of nuclear densities. Ratio of nuclear densities of two elements of uranium 235 and hydrogen is 1:1. So it doesn't even change, remain the same. How much is that? 2.3 in 10 power 17 kilogram per meter cube. You can check the same thing in the NCERT textbook. Now, given the mass of the iron nucleus is 55.85 U. Children, what is U? We have seen, no? Atomic mass unit. What is the value of one atomic mass unit? We have seen. All that you have to note it. One atomic mass unit, 1.66 in 10 power minus 27 kilogram. So same thing here we are looking at. So nuclear density for iron nucleus, same thing. So 9.27 mass of iron and then mass of this 55.85. When you multiply you get the same thing. So nuclear density is going to be the same. So the density of matter in neutron stars is comparable to this density. This shows that matter in this object has been compressed to such an extent that they resembled a big nucleus. Okay, we will go to the next one. Einstein mass energy relation. Einstein's mass energy relation. Mass energy relation. So according to Einstein, the equivalence of mass energy relation, the energy equivalent of mass is related by the equation E is equal to delta m into c square. So what is delta m? This delta m is nothing but a famous terminology called as mass defect. Have you ever learnt about mass defect? We have been studying from the lower classes. Mass is neither created nor destroyed, but Einstein is the one and only scientist says that mass and energy are interconvertible. So therefore There is a relation between the mass and energy, that is energy E is equal to delta m into c square, where c is the speed of the light in vacuum, that is equal to 3 into 10 power 8 meter per second, that is velocity of the light in vacuum. Velocity of the light in vacuum. So, the energy relation between the mass and the energy released during the reactions is interconvertible according to Einstein, that is equal to delta m c square. Calculate the energy equivalent of 1 gram of a substance. So, we know that E is equal to delta m into c square or mc square. 1 gram of a substance, 1 into 10 power minus 3 kilogram into c square, that is 3 into 10 power 8 the whole square. When you multiply, you get 9 into 10 power 13 joules. So, 1 gram of a matter is converted to energy, there is a release of amount of energy 9 into 10 power 13 joules. That is what it means. Now, find the energy equivalent to 1 atomic mass unit. 1 atomic mass unit, I am going to write it in terms of 1 electron volt. We already know that 1 atomic mass unit is nothing but 1.66 in 10 power minus 27 kilogram, which you have already learnt. But this mass to be converted into energy. So, we have already seen according to Einstein mass energy relation, just now only we saw, that is equal to mc square. So, that is equal to 1.6 in 10 power minus 27 into 3 into 10 power 8 the whole square. So, when you multiply this, and then you will get 1.66 into 10 power minus 27 into 10 power 16 into 9. So, that is equal to 1.66 into 9 approximately 1.6 into 10. So, that will be approximately equal to, this is 1.49, that is 1.5, approximately equal to 1.49 into 10 power minus 10 joules. So, I found out in joules, but I wanted to convert into electron volt. We know that 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Put it in other way around. For 1.6 into 10 power minus 19 joules, it is 1 electron volt. So, I put it in other way around like that. If it is 1.6 into 10 power minus 19 joules, it is 1 electron volt. Therefore, 1.49 into 10 power minus 10 joules, how much is the electron volt? So, if you get it like that, you get 931.15 mega electron volt you will get. How much you get? 931.5 mega electron volt you get. So, therefore, you can say that 1 atomic mass unit is equal to 931.5 mega electron volt per c square, that is the standard value. How you know standard value for K, force constant? 9 into 10 power 9 Newton meter square per coulomb square. So, how you know epsilon naught permittivity? 8.8 into 10 power minus 12 coulomb square per Newton meter square. Same way, you have to know 1 atomic mass unit in kilogram, that is 1.6 in 10 power minus 27 kilogram. How did we define 1 atomic mass unit? In terms of carbon 12 atom, mass of 1/12 of the mass of carbon 12. We have learned to know. But how do you write in terms of electron volt? That is all. 1 atomic mass unit is equal to 931.5 mega electron volt per c square. So, keep that in mind, children, hereafter. Next, I am going to discuss about mass defect. Mass defect. For determining mass defect delta m, I am going to give you an example. What example? You must have learned, you must have seen laddu. How laddu is made? Tirupati laddu is there, no? So, how laddu is made? The laddu, lot of bundis are there. So, lot of bundis, first of all, you have to make it, all these are separate bundis. Add some flavors, that is nothing but sugar liquid. When you add flavors, after that it becomes laddu. You must have noticed that in the laddu, all the bundis are bounded up together very tightly. While you are making laddu, some laddus, some bundi would have been wasted. Some mass would have been wasted. Why it is wasted? It is not wasted actually, would have been utilized. Why to utilize it? Because you require some amount of energy to bind up all the bundi together. Earlier it was free, bundi is free. Is it free? Yes. Now what happened? All bundis are binded up. It is bounded tightly. In order to bound it tightly, you require some external energy. You require some external energy. You require somebody should just give some energy to bind it, but there is no some external energy. Therefore, it by itself is taking. What is that? In order to bind all the nucleons together inside the nucleus, some mass has been, some mass would have been utilized or converted into energy. Some mass is converted into energy. Why do we need energy? Energy to bind up the nucleon together. To bind up the nucleons. What are nucleons? Proton and neutron. Nucleons together inside the nucleus. Together inside the nucleus. That is all, children. Very simple. Neutron and proton are called as bundi. This neutron or proton are called as bundi, that is freely, in free state it is there. Now what happened? The neutron and proton are going to be bounded up in nucleus. So laddu, while you are making laddu, in order to bind up this bundis together, you require some amount of energy. Same way, in order to bind up this neutron and proton together, you require some amount of energy. So that energy is taken up from its own mass itself. So some of the mass would have been converted into energy. So according to Einstein, that is nothing but, that energy is nothing but binding energy. What energy? Binding energy. So that binding energy is nothing but, some mass has been converted, no? So how can you find out that mass? You difference between the original mass of neutron and proton and mass of the nucleus. Subtract both, you get the mass. So that is equal to delta m into c square. So very simple. What is mass defect? Difference between the mass of, difference between the mass of nucleons, mass of nucleus, difference between the mass of nucleons and the nucleus, mass of constituent nucleons and the nucleus. You call it as mass defect. Okay, the difference between the mass. So now how do we find out the mass? Let Z is equal to atomic number. That is nothing but what, children? Number of protons. Okay, right? What is A, children? A is nothing but atomic mass. Atomic mass is nothing but number of protons plus what? Number of neutrons. Be careful. Number of neutrons plus protons. Next, A minus Z. Subtract both. That will be equal to number of neutrons. I know number of neutron, I know number of protons. Let MP is equal to mass of proton. Listen carefully, children. And Mn is equal to mass of neutron. And you take capital M is equal to mass of nucleus. So therefore I can write delta M is equal to mass defect. Mass defect. That is nothing but mass of nucleons minus mass of nucleus. Nucleons are the one which is present inside the nucleus. But it has been formed by combination of protons and neutron together. A proton and neutron fuse together to form the nucleus minus mass of nucleus. So therefore I can write mass of nucleons is nothing but sum of mass of proton and neutron. So mass of proton into number of proton. So let me write like that. Z into MP plus mass of neutron into, what is mass of neutron? A minus Z into mass of neutron minus mass of the nucleus. That's all. Very simple. Therefore binding energy Binding energy is nothing but energy required to bind up the nucleus. But we won't be knowing. You break the nucleus and find out the energy that is equivalent to energy required to bind up the nucleus. Binding energy is defined as the energy required to dissociate nucleons from the nucleus. You break the nucleons from the nucleus. Therefore, I can write binding energy is equal to delta M into C square joules. Or I can write binding energy is equal to delta M into 931.5 mega electron volt. So, instead of these joules, I am writing, because I have already known that mega electron volt. How we calculated in terms of mega electron volt. What is 1 U in mega electron volt? 931.5 mega electron. Same way I am writing here. So, in mega electron volt, I have converted this joules into. So, we know that binding energy. So, literally we know that what is mass defect and what is binding energy. So, now one such example is given using this expression, express the mass defect of oxygen. 16 in mega electron volt. So, now delta M value you have to find out, mass defect. So, how do we find out delta M value? So, we will find out that mass defect. We will take yes. So, how to find out the mass defect? We will see here. It is very simple, children. Mass defect. So, what is delta M is equal to mass of nucleons minus mass of nucleus. That is all. So, how many protons and neutrons are there? You can say number of protons, Z value is equal to 8. Then what is A minus Z value? That is equal to 16 minus 8. So, that is equal to 8. So, therefore, delta M is equal to mass of the proton into number of protons plus mass of the neutron into number of neutrons minus mass of the nucleus. Mass of the nucleus is already should have been given, mass of the nucleus, that is oxygen atom, mass of the nucleus. From the table you can find out. So, directly it is given delta M. So, when you multiply that, delta M in the NCERT textbook, mass of the proton is given and mass of the neutron is given. So, you can utilize the same thing from the NCERT textbook. We will check the same thing. Yeah, here. Can you check here? This is mass of the proton. The whole table you can see, utilize it. Okay, so here everything is given. Yeah. So, this is the table we are going to use it. So, by using the table, I think you will be able to find out, that is oxygen 8, 16. So, therefore, delta M is equal to 8 into mass of the proton. So, what is mass of the proton? 1.007825. So, that is mass of the proton plus 8 into mass of the neutron, 1.008665. Add both first, very simple. Just addition, subtraction, and getting the answer. Minus mass of the oxygen atom. So that would have been given in the question itself. Mass of the oxygen atom, where it is given. So nowhere it is given. Here. We will check in the NCERT textbook. That is mass of hydrogen atom. Mass of oxygen atom. 15 point something it would have been given. So when you multiply, I think you have to go above the book and then you find out what is mass of the oxygen atom. Definitely it would have been given. In the question paper also it will be given. You don't need to bother about it. So here, yeah, it is given. Can you check here? So this 16.127 nucleus, that is 16.12744. No, 15.99493 atomic mass. 15.99493. You can check here. So now, so I can take the same thing here and yeah, so 15.99493 U. Okay children, it's very simple. So I can subtract with the 15 point, so quickly let us learn 99493 U. So when you multiply this and then add with this and subtract with that, then you will get the same answer, that is delta M 0.13691. So that's all. So delta M 0.13691 U. So therefore I know delta M, therefore binding energy is equal to delta M into 931.5 mega electron volt. See here, 931 mega electron volt per c square. So 127.5. So that is equal to, you will get 121.5 mega electron volt. Check here, 127.5 mega electron volt per c square. That is all children, binding energy. So likewise you can find out. So we know binding energy and we know mass defect. Now we are diving into the topic, next topic, that is nothing but binding energy per nucleon. What is the next topic? Binding energy per nucleon. What is the necessity of learning binding energy per nucleon? In order to find out the stability of nucleus. This is specially to find out the stability of nucleus. To find the stability of nucleus. How do you find out the stability of nucleus? Only by knowing the binding energy per nucleon value. Only by knowing the binding energy per nucleon value. If B by A, that is binding energy per nucleon, is more, then the atom is said to be, more stable. More stable. For example, the value of Be by A, you can't find out by using binding energy. For example, certain element binding energy value will be more. But you can't conclude that since the binding energy value is more, stability is more. How do we find out the stability? Only by using binding energy per nucleon value. So the value of binding energy per nucleon for iron nucleus, Fe56 nucleus, iron nucleus is 8.8 mega electron volt. So therefore it is said to be most stable element. It is said to be most stable element. If you want to see the stability of the element, rough plot of binding energy per nucleon value will give you an idea, just a rough plot. So it is said to be most stable element. So we will see that rough plot of binding energy per nucleon value versus mass number. So it has been roughly determined that you can see that binding energy per nucleon value over here. It is almost, these elements are almost higher value. and these elements are lower values except the recurrent peak elements. These elements are lower value binding energy. That's nothing but almost all the lighter nuclei element. Lighter mass number elements are almost unstable. Similarly, heavier mass number elements are unstable and except a few elements. So from this one can determine which is stable and which is unstable. So it is just rough plot. It has been found out that elements having mass number A less than 0 less than A less than 30. So that is nothing but mass number between 0 to 30 are unstable. Mass number between 0 to 30 are unstable except a few recurrent peak elements. From the figure, from the graph, you can find out except H12 that is stable, H13 that is slightly stable, then lithium, hydrogen, helium, then carbon, nitrogen, then oxygen, sulfur, all these are almost stable. Okay, how can you find out almost stable? That is a strategy to find out. Look at the mass number and the atomic number. 2, 1, 4, 2, 12, 6, 14, 7, 16, 18. Look at that number of neutrons, proton ratio. Almost stable. How can you find out? Neutron to proton ratio you find out. N by P ratio almost equal to 1. Almost. For example, what is number of neutrons here? Number of neutrons over here is 1. So 1 is to 1. Here number of neutron is 2. 2 is 2. So number of neutron is 6. 6 is to 6. 1. So number of neutron is 7. So therefore neutron to proton ratio is 1 almost. If N by P ratio is almost equal to 1, then it is stable. You understand, children? See how to find out certain elements are stable. For example, I have taken hydrogen, helium, carbon, nitrogen, oxygen, sulfur. Please listen carefully. You will get an idea. You find out the number of neutron. How do we find out number of neutron? For example, I am taking H12. How much is the number of proton? Number of proton is equal to 1. How much is the number of neutron? How do you find out number of neutron? Mass number minus atomic number. So 2 minus 1. So I am getting 1. So what is N by P ratio? Number of neutron to proton ratio. Tell me now, what is the ratio? 1 is to 1. Similarly, you take carbon 612. What is number of neutron? Proton. Proton is equal to 6. Neutron is equal to 12 minus 6. That's equal to 6. So therefore N by P ratio is equal to 1. If N by P ratio is equal to 1, then it is almost stable. So such elements only I have taken. So you should say mass number 0 to 30 are unstable. Okay, they are unstable. Then how will they attain stability? Very simple. Attain stability to increase the binding energy per nucleon value. Attain stability to increase binding energy per nucleon value by undergoing nuclear fusion reaction. This is nuclear fusion. Okay, right. What about 30 to 170? What about 30 to 170? The 30 to 170 elements are almost stable. So therefore I can say number 2, elements having 30 to 170, 30 less than A less than 170 are almost stable. Almost stable. Average binding energy per nucleon value. Average binding energy per nucleon value comes around to be 8.5 MeV. Hence, you can say that almost all the elements are stable. Example, most stable element we have already discussed. Same thing, most stable element is iron 56, which is equal to 8.8 MeV. Next, mass number greater than 170 are unstable except few elements. I'll have one such elements we have taken, that is uranium 238, okay, or tungsten 184. So I'll take except uranium 238. Except uranium 238, almost all other elements are unstable, attain stability. By increasing its binding energy per nucleon value, by undergoing by nuclear fission reaction. There it is fusion, here it is fission reaction. So energy is released here. So fusion reaction, here it is fission reaction. They attain stability by undergoing nuclear fission reaction. Children, you must understand that inside the nucleus, the protons and neutrons are tightly bound together. Similarly, protons and protons are tightly bound together with the help of a new force called as. There is a force which is not to be seen or not to be calculated by mathematical calculations, but there exists. Without the presence of that force, no nucleus can be bounded together. That force you call it as nuclear force. It says that why only these elements are stable, because these nuclear forces are going to be a very short range force. Short range, only for the shortest distance the nuclear force is going to be very strong. It binds up the nucleon together. So therefore that nuclear force only we are going to talk about. So there is a connection with this binding energy per nucleon value and this one. So the stability of binding, the constancy of binding energy per nucleon gives constancy of binding energy per nucleon value for A is equal to A between, for mass number between 30 to 170 reveals that nuclear force is short range force. So what are nuclear force? You must know what are nuclear force. Nuclear force is nothing but the force which binds up the nucleon together. Force exists between neutron and neutron, proton and proton, and proton and neutron, which binds the nucleon together, together inside the nucleus. Nucleon together tightly inside the nucleus. So this type of force is very much attractive. It attracts. Neutron is chargeless. Proton is positive charge. You may be wondering, proton is positive, proton is positive and positive repel. That is all only outside the nucleus. But inside the nucleus, the dominating force is the strongest force. That's nothing but the nuclear force, which is always attractive, which is independent of the charge. So the force is attractive. And properties of nuclear force. So for example, one proton is here, another proton is here. When this proton come closer together, now what happened? The repulsive force is dominating. But when it is coming very closer, this proton, the repulsive force, Coulomb's repulsive force is negligible. That is a strong attractive force which is happening. That is nothing but nuclear force. So therefore you can say it is not only proton and proton, it is also proton and neutron. So when it is far away, it gets attractive, but when it is closer and closer, what will happen? It repels. It is attractive when it is far away. Far away, it is attractive. Attract. But when it is closer, what will happen? The strong repulsive force exists. Very strong repulsive force exists, which it just like an elastic rubber band. It holds the nucleon together. So therefore, when it is coming very closer together, what will happen? A strong repulsive force exists. So therefore, you can say that properties of nuclear force. It is a very strong force. And it is a short range force because it exists only up to certain femtometer, 10 power minus 15 meter. After that, it gets weakened. When it goes far and far beyond, the neutrons are far away, what happens? The nuclear force is not that much intense. When it is coming closer and closer, what will happen? There will be a nuclear force which is acting between these two, which bound up very tightly. A strong repulsive force exists and it bound up inside the nucleus. So short range force. You can't say that, oh, from this distance, this much nuclear force. So it is inversely proportional. Nothing like that. For certain distance up to 0 to 10 power minus 15 meter, 0 to 0.8 into 10 power 15 meter, the nuclear force from A to B remain the same. The value remain the same. But beyond B, if the proton or the proton is going beyond B, the nuclear force is nullified, vanished. Then Coulomb's force will dominate. So it will be acting only for a shortest distance, therefore short range force, and it is always maximum, that is called saturated force. And the charge independent force, mainly charge independent force, strong force, short range force or charge independent force. And non-central force, non-central. So these are the very, very important properties of the nuclear force. So this nuclear force graph says here, like you have to draw in such a way that up to, I have already told you, 0.8 Fermi. This is potential energy of pair of nucleon versus distance r. So potential energy of pair of nucleons, energy existing between the two nucleons. So when r is greater than r naught, I have already told you when protons are far away, attractive force. Here I will write attractive force. When it is coming very closer and closer, repulsive force. So like this only you should draw. Here you could have given 0, it is above potential energy in mega electron volt, and R is in Fermi. Exactly 0.8 Fermi till this repulsive force acts. After that it becomes weakened. So therefore you can say that attractive force. So I know the nuclear force. Now about nuclear fission. This is all very simple, children. Nuclear fission is nothing but breaking up of nucleus. Uranium-235, once after bombarding with a neutron, it breaks into barium, krypton, 3 other neutron. You may be wondering, is it only barium and krypton? No, depending upon the energy. So can we check nuclear fission and then fusion? So the disintegration of energy in fission, the neutron, after bombarding with the neutron, the uranium-235 becomes uranium-236. And then it split into barium and krypton depending upon the energy. You can see here, let us take nucleus A240. So this is A240. It is breaking into 2 fragments, that is B and C. B is 120, here also 120. But the binding energy for A is 7.6 MeV. And binding energy for 2 fragments is 8.5 MeV. This is one 8.5 MeV, 2 fragments. This is 8.5 MeV. Together it is 8.5 MeV. Together. So therefore what is the difference in binding energy? 8.5 minus 7.6 MeV, that is equal to 0.9 MeV. That is gain in the binding energy of nucleons. There is a gain in the binding energy of nucleons in fission. So therefore, binding energy is 240 into 0.9, because all this whatever we found out is binding energy per nucleon is 0.9 MeV. So therefore, binding energy is equal to what? Binding energy per nucleon is 0.9 MeV. Binding energy is equal to 0.9 MeV into A. What is A given? 240. So 0.9 into 240 MeV. So that is equal to 216 MeV. Total gain in the binding energy. So give an example of nuclear fission atom bomb. Same way here, nuclear fusion. When two lighter nuclei fuse to form a larger nucleus, then nuclear energy is released. So therefore, such large energy, since the larger nucleus is more tightly bound, the energy liberating nuclear fusion reaction is been like that. I am going to show you that. So you can see how the nuclear fission and fusion is taking place. Yeah. So this one, 4 hydrogen atom. Children, 4 hydrogen atoms. See here, I am taking it. Fuse together to form. See here, the 4 hydrogen atom fusing together to form. See, all 4 is fusing. See here, all 4 is fusing. So nicely done the stimulation. Wow. All 4 hydrogen atom fuse to form deuterium. Now again you see deuterium plus electron release with the neutrino. Now again you see, again so good, so nice. So the 2 deuterium nuclei again fusing together to form tritium, helium 2, 3. Check, so good. Now again what happens? Check. Then again this helium 2, 3 isotope of helium again forms helium 2, 4 with enormous amount of energy. Wow. Again what is happening? Helium once happen becomes hydrogen because of the strong gravitational force. Then this process taking place. Do you understand, children? So likewise, decay chain, uranium decay chain. You can see here uranium, thorium, then again beta particle, then again emission of alpha particle, thorium, radium. So it just goes on, it's chain continuous. So you can see here it is continuous. So this process is being continuous. This is called as nuclear fission reaction. So hope you understand this, children, nuclear fusion and fission. And the last one I would like to just narrate about the nuclear fusion. We have already seen that the neutron combined to form the lighter isotope of helium. In reaction, 2 deuterons combine to form triton and proton. For fusion to take place, the 2 nuclei must come closer enough so that attractive short range nuclear force is able to affect them. It has to come very much closer enough. It requires large amount of energy. So that, however, since they are both positively charged particles, they experience Coulomb's repulsion. Which one? The isotope of deuterons. 2 deuterons are positive. When they come closer and closer, Coulomb's repulsive force is dominating. Hence, they experience Coulomb's repulsive force. They will not be able to fuse. Somehow they have to fuse now, one positive. How is it coming closer together? No, right? That means it has to overcome the Coulomb's repulsive force. In order to overcome, it has to break the barrier. In order to overcome, you have to give enough energy to overcome this Coulomb's barrier. The height of the barrier depends upon the charges and radii of the 2 interacting nuclei. So barrier height depends upon number 1, charges, and number 2, radii of interacting nuclei. it can be shown that the barrier height for two proton, barrier height for two protons is about 400 kilo electron volt. This much energy required, and is higher for nuclei with higher charges. So barrier height, in order to overcome, see, two protons are coming together. I am talking about fusion. Listen very carefully. It's very simple. So it will be asked in one more question. During fusion, repulsive force will dominate, Coulomb's repulsive force. How is that the charged particles are fusing? You have to say that charged particle, to fuse, energy has to be given to overcome this barrier. So the barrier height depends upon the charges and radius. For example, the barrier height for two proton is 400 kilo electron volt, and it is higher for a nucleus with higher charges. We can estimate the temperature at which two protons would have enough energy to overcome. How can you estimate? 3/2 kBT is equal to, last year class 11 you would have learnt thermal kinetic energy in thermodynamics. So 3/2 kBT is nothing but law of equipartition of energy. So this energy will determine the temperature, so that will be equal to 400 kilo electron volt. When you substitute, the T will comes around to be 3 into 10 power 9 Kelvin. When fusion is achieved by raising the temperature, the particles will have enough kinetic energy to overcome the Coulomb's repulsive force. Therefore, this is called thermonuclear fusion. So understand, children, for thermonuclear fusion is nothing but, in order to fuse two nuclei require large amount of energy. That can be achieved by increasing or raising the temperature. That temperature comes around to be predominantly high, and that too if the barrier height is going to be more for more charges or more radius element, then you have to give more amount of energy, more amount of temperature. Thermonuclear fusion is the source of energy output in the interior of stars. The interior of the sun has a temperature of 1.5 into 10 power 7 Kelvin, which is lesser than this. Therefore, fusion in the sun involves proton whose energies are much above the average energy. So fusion takes place only if the protons would have energy greater than that of the average energy. So therefore, the fusion reaction in the sun is a multi-step process. So it is not one single process like proton and proton, it's combined. It is a multi-step process in which hydrogen is burned into helium. Hydrogen is burned into helium. Thus, fuel in the sun is the hydrogen in its core. So hydrogen is present in the core. The proton-proton cycle by which this occurs is represented by the following sets of reaction. So 4 hydrogen atom combine together to produce helium. So 4 hydrogen plus 4 electron will give helium. Thus for hydrogen atom combine with release of 26.7 mega electron volt of energy. So helium is not only the element that can be synthesized in the interior of the star. Hydrogen is converted into helium. Helium is not only the element. As the hydrogen in the core gets depleted and becomes helium. Now only we saw, right? Hydrogen in the core become depleted and become helium. The star begin to collapse under its own gravity. So we have seen now once again I will show you that. See here, the hydrogen, it is becoming helium. So now once after becoming helium, star try to collapse. Once after collapsing, what happens here? Once after collapsing, you come here to this. It collapses. Again, higher mass of elements, fusion takes place. Own gravity which increases the temperature. Star begin to collapse under this own gravity which increases the temperature. As hydrogen in the core get depleted and become helium, then the core start to cool. The core cool now. Once after cooling, what happened? The star began to collapse under its own gravity. It's collided and becomes cooled, right? Then If the temperature increases to about 10 power 8 Kelvin, then fusion again takes place. This time helium nuclei converted into carbon. Hydrogen become helium. Now when hydrogen becoming helium, the core starts to cool because of its own gravity. The star begin to collapse. When the star is begin to collapse, increases the temperature. And when it reaches 10 power 8 Kelvin, then this time helium nuclei is converted into carbon. This kind of process can generate through fusion higher and higher mass number of elements. But elements more massive than those near the peak of the binding energy curve cannot be so produced. So all these insights you have to learn, children. So that is all. Now this is this you can learn how can an electric lamp of 100 watt be kept. So use that power is equal to energy by time taken. First you find out energy, then is equal to power into time. So like that you can find out by using this. Thank you, children. I will see you in the next class. Learn all these insights, and the next class we will see the problems.